In this video, we're going to talk a little bit about the total energy of a particle. So let's consider that you have some object, some particle, that has some mass, and it's moving with a velocity v. This is the idea or the construct of a point particle, which is how we often think about things in physics, because we don't care about all the details of the motion. We might just care about how an object is translating. So we're going to talk a little bit about what the energy of that looks like. So thanks to Einstein, we know that the total energy of that particle is gamma mc squared, where gamma is our old friend 1 over the square root of 1 minus v squared over c squared. Now, this is the full description of the total energy of a particle. But what's kind of interesting is if you say, let's set the speed to 0 so that the object is not moving, right? What happens to gamma in that case is it goes to 1. And so there's still some energy associated with an object that is not moving. This is the so-called rest energy. And this is the famous formula due to Einstein, which is that the energy of a particle at rest is mc squared. This is the total energy that it has. This is the energy due to it just having mass. And so there must be some difference here which accounts for the motion. And that's the so-called kinetic energy, which we'll represent with a k. And that's the difference between the total energy and the rest energy. So that's simply gamma minus 1 mc squared. So for objects of all types, anything that is moving, this is the full description of the kinetic energy of that particle, gamma minus 1 mc squared. This might not be what you're used to seeing if you've taken other physics courses or if you've read along in various other textbooks. What we normally think of as the kinetic energy is actually a simplification of this formula. If instead you're worried about when the velocity or the speed is much less than the speed of light, what you get is that gamma becomes 1 minus v squared over c squared, roughly, and we're subtracting off 1 there, times mc squared. And so what you end up with is a half mv squared. This is for objects which are moving much slower than the speed of light. So most of your sort of terrestrial objects you'll worry about here. Particles, very small particles that are moving very quickly, you have to use this. This will work for anything, but it involves a little bit more math. This will work for anything that's moving fairly slowly, where gamma can be basically approximated to be 1. So this is kind of useful because we can put this back into our energy equation, our energy principle equation, which is that the change in energy of a system is equal to the work done by the surroundings plus the exchange of thermal energy, the heat. So we're going to make some simplifications to this. We're going to talk about just a single particle. So we're going to look at the change in the total energy. And then we're going to take situations where we're not worried about the thermal energy change. And so this is going to become a little bit simpler, because what we're going to do is we're going to track the total energy and how that changes with just works that are done by the surroundings. I'm going to get rid of a little bit of this so we can talk a little bit more about this energy equation. I'll leave this part here. And so what we have is that the total energy change of a point particle, where we don't care about the thermal energy change, is equal to the work done by the surroundings. So again, no thermal energy change. So this is really a point particle approximation, because a point particle, we're just concerned about the translation. We don't care about any internal structure that it has. So if we look at how this total energy is going to change, the rest energy will change, and the kinetic energy will change in response to any work that's done. Now, for the time being, we're also going to allow the rest energy to remain the same. It is not going to change. The particle will not change its mass, which is what would happen in a situation where the rest energy changes. So what we're going to say is that the mass is a constant. Particle doesn't change its identity. And what that leaves us with is the conservation of energy in its most simple form. That is, that the work done by the surroundings relates to the change in kinetic energy of the particle. So this is conservation of energy in the most simple form that we can think of it. One thing that allows us to do is make predictions about how the kinetic energy is going to be given some initial conditions. So the change in kinetic energy is equal to the work that's done. Therefore, K final minus K initial is equal to the work that's done. We can move this equation around a little bit, and we can predict what the kinetic energy is going to be given whatever it was initially plus whatever work is done. So this is the update form of the kinetic energy work theorem, or the energy principle in its simplest form. You might notice that this seems very similar to another equation that you had that was a prediction equation. This was the momentum prediction, which is P final is equal to P initial plus the net force times delta T, where this is actually due to the surroundings. So you can see a very similar analogy here, and actually the analogy extends pretty far. If we know about the impulse that the surroundings delivers, the force times the time, I can tell you what the new momentum